In this section, we're going to take a brief look at some of the findings that have led to our understanding of atomic structure. By the late 1700s, John Dalton had articulated the basic ideas of the modern atomic theory: that each element is composed of a unique type of atom, that atoms could combine in whole number ratios to form compounds, and that compounds were not created or destroyed in chemical reactions. However, essentially nothing was known about the structure of the atom. Perhaps the first major step to understanding atomic structure came in 1800 when Alessandro Volta invented the first electrochemical cell, that is, the first battery, by placing plates of zinc and copper on either side of a medium of sulfuric acid. Within a year, others had used the electric current to split water into hydrogen and oxygen. In the following years, a number of new elements would be discovered as scientists exploring the uses of electricity were able to reduce metals or oxidize nonmetal ions to their elemental forms. In particular, Michael Faraday made tremendous contributions to both chemistry and physics, and is considered to be the father of the field of electrochemistry. By the late 1800s, scientists had developed a device called the cathode ray tube, or CRT, which made remarkable contributions to our understanding of atomic theory, and which would form the basis for television monitors and other devices well into the 21st century. Essentially, a cathode ray tube is an evacuated tube with a negative electrode, or cathode, at one end, and a positive electrode at the other end. When connected to a power source, electricity can flow from the cathode towards the anode. Much like lightning, the flow of electricity through the tube excites the tiny amount of gas present, causing it to glow where the beam of electricity is focused. Often the CRT is lined with a fluorescent material, causing the glass to glow when electrons hit it. In 1897, J.J. Thomson discovered that if he placed an electric or magnetic field near the CRT, the beam of electrons could actually be deflected. Similar deflections had already been observed with hydrogen ions, H+ ions, but Thomson noticed that the deflection number 1 was in the opposite direction and 2 substantially greater than that observed for H+. Based on the degree of deflection, he was able to determine the ratio of mass to charge for the electron. Subsequent to Thomson's experiments, Robert Millikan, a physicist at the University of Chicago, was able to measure the charge of an electron by measuring the motion of charged oil droplets falling through an electric field. Once the charge was determined, it was simple, based on Thomson's experiments, to determine the mass of the electron. The mass of the electron was found to be approximately 1/2000th the mass of the hydrogen atom. At approximately the same time as the Thomson experiments, William Röntgen, a German physicist, discovered X-rays. In fact, his first X-ray photo, taken in November of 1895, was of his wife's hand. This image is shown here. In the same year, Antoine Becquerel discovered radioactivity. In the years that followed, Marie Curie and her husband Pierre worked extensively to isolate and characterize radioactive substances. Curie found that there were 3 major types of radioactivity. When passed through an electric field, one type, termed alpha radiation, was found to deflect towards the negative plate, indicating a positive charge. The second type, beta radiation, deflected the opposite direction, indicating a negative charge. The third type, gamma, did not deflect as it passed through the electric field, and therefore was deemed to have no charge. Today, we know that alpha radiation is essentially a helium nucleus. It has a mass of approximately 4 atomic mass units and a charge of +2. Beta radiation, on the other hand, consists of high-energy electrons. It has a mass of approximately 0.0005 atomic mass units and a charge of -1. We now know that gamma radiation is just a burst of electromagnetic energy. It has no mass and no charge. Despite these findings, scientists in the early 1900s still did not have a clear picture of atomic structure. A key finding came in 1911 when Ernst Rutherford performed his famous gold foil experiment. Using a source of alpha radiation placed inside a lead cylinder, Rutherford wanted to study the deflection pattern the particles made when they bounced off a thin gold film. In order to study this, he surrounded the film by a fluorescent material, which would emit a flash when the radioactive particles struck it. Rutherford expected most of the particles to deflect off the film and hit the front portion of the screen. While some flashes were observed in these locations, most of the flashes were seen immediately behind the gold film. That is, the alpha particles had passed straight through. This led Rutherford to postulate that most of the atom was empty space, and this empty space allowed the particles to pass through the film. We now know that in fact Rutherford was right. The atom is almost entirely empty space. We often draw atoms as a nucleus surrounded by orbiting electrons. However, these pictures are never drawn to scale. Although the nucleus contains almost all the mass in the atom, it's incredibly dense. It's been said that the size of the nucleus compared to the volume of the atom is comparable to the size of a butterfly inside a football stadium. Ultimately, these and other findings have led to our current understanding of atoms, that the nucleus is composed of two particles, positively charged protons and uncharged neutrons. Orbiting the nucleus are the electrons, tiny particles with a negative charge. We'll explore more about both nuclear and electronic structure in subsequent sections.